postdoc at UCLA, sorry, and then distinguished PKS postdoctoral fellow in Dresden at the Max Planck Institute, and also a junior group leader in Leibniz at the Institute for Solid State and Materials Research. And her research focuses on emergent dynamics and transport phenomena in quantum materials and platforms, and it's a pleasure to have you here and to listen to your work.
Thank you very much for the introduction, and thanks for the great hospitality. It's a very nice place to be. It's my pleasure to share with you some of my recent work. So it's published earlier this year, a work done together with Shovan Dutta, who was a postdoc also in Dresden and now moved to India, and also Masoud Haka, who's affiliated with PKS and also TU Dresden. So it's about some Liouvillean spectral signatures of classical attractors. So I'll show you how to bridge this quantum and classical regime. Okay, so the starting point is basically, on the one hand, we know how to describe a Markovan open quantum system. We have this nice formalism of Lindbladian, where you can look at the exact magnetization of the Liouvillean spectrum. And on the other hand, in the classical dynamics, we know there are some very interesting things, especially when you have nonlinearity. You can have attractors, and for limit cycle, there's persistent oscillation. So these are quite interesting phenomena. And if we think about microscopic model, right, and everything in principle has a quantum origin. So how do you go to a classical limit that has nonlinearity and these interesting attractor physics? So this is like from quantum origin to the classical limit. And the other way, you can also ask the question, if we have some interesting classical equations of motion, can we construct a Lindbladian description that will give me these equations of motions in the classical limit? And if not, now I look at the Liouvillean spectrum of this Lindbladian, can I find some features in the spectrum? And the hope is that these features can be universal in the low decay rate part, right? If you look at the complex spectrum and we focus near the imaginary axis, where the real part is close to zero, can we find some universal features? So this is basically the point of this paper, that in the case of limit cycle, so on the left side is the, in the quantum regime, you will see a parabolic branch. So this branch here. Then in the classical limit, this branch collapses onto the imaginary axis, and this gives rise to a limit cycle. And I will also show you in the case of Hawk bifurcation. So basically, when you go from a fixed point to the limit cycle, during this transition, there is a bifurcation. Something similar happens, and you have a large chunk of the spectrum. They all collapse onto the imaginary axis. So these are like interesting spectral features of this classical attractor dynamics. Okay, and there are several motivations to think about this question. One is that we know the information in the spectrum is very useful. In the case of Hermitian physics, when you look at the energy levels of a Hamiltonian system, so you can look at the statistics of level spacing ratio to predict whether the dynamics is integrable or chaotic. So this is a very important judging standard. And similarly, in non-Hermitian systems, there are a recent work on the trying to define a similar thing as level spacing ratios, but for complex energies. And there's some nice work on this aspect. So if you look at the typical Leucian spectrum, right, it sits on the negative real part of the complex plane. And usually there is a unique steady state in the most generic case. But also you can have degeneracy, for example, if there's symmetry and there could be some oscillatory modes that has zero real part but finite imaginary part, and usually there is a gap that separates these modes from the rest. Those are the decay modes. And this is a typical scenario we see. But if we think that, right, there's always this gap, so most of the things will decay away, is it possible to have a persistent oscillation if we take the classical limit? So in classical limits, there could be a limit cycle that looks like this, right? So this is a very simple model. You can get the limit cycle. Basically, wherever you start, you're attracted to this circle, and you will have persistent oscillation. And we would like to think of this in a very generic setup, like I don't have any symmetry that impose such right, these degenerate steady state or steady state that sits on the imaginary part, but like in a way that's guaranteed by the nonlinearity in the problem. Right, so here I would like to contrast the two scenarios. So one, you have symmetry protected degeneracy, so it will depend on where the initial state is, which final state, which steady state you will arrive at. And this limit cycle that's given by the nonlinearity in the problem that doesn't rely on the initial state. You're always attracted to this circle. And so why are we interested in persistent oscillation? There's some connection with time crystal physics. And this is a nice paper that shows this boundary time crystal. And if you look at the spectrum there, there is a collapse of the gap as you go to thermodynamic limit. So if you track right, these low energy states, they will the gap will close for all of these points in the thermodynamic limit. And a third motivation, maybe a bit interdisciplinary, is like I have a background in spintronics, and there we also think about driven dissipative dynamics in a slightly different way. So I can say I have a spin which has a damping, like a viscosity term, and then I can pump it with some current. And if the damping and pumping nicely cancel each other, you can get a limit cycle, a persistent oscillation in the spin dynamics. And a question to ask would be, can I have a Lambda description of such an equation of motion? So some of my work goes into the direction of bridging quantum optics with spintronics. For example, this is one that we consider the analogy between a cavity QED problem and a typical spintronic setup with heterostructure. So you have two species of spins. Here in the heterostructure, you can say I have the spins from the itinerant electrons in the metal, and also another species of spins that's localized in a magnetic insulator. And they can interact through some long wavelength mode, and that looks like a photon mode in the cavity. So there are some quite interesting dynamical phase transitions in this setup. And also we can think about how to model spin dynamics in an open quantum system that has quite nice application in quantum sensing. So the Lindbladian can give you the description of how a qubit sensor works. And if we put it close to other materials, which is like a bath, right, you can think what features I would say in the qubit relaxation that can tell us information about the bath. So there's some examples. We looked at features of spin diffusion in magnet insulators, and also valley. So it's a pseudo spin degree of freedom in topological materials, and also magnetic BKT transitions in 2D magnets. And it's also reasonable to think about larger spin, not just qubit. A larger spin can be made of like a high spin state in a quantum dot, or if you have a bunch of spins that strongly interact with each other with Fermat interaction, so they form a large spin. And in these platforms, they can also be driven in some way, and their dynamics is distributive, so it seems to be going in the direction of open quantum system description. Yeah, so these are things to explore. So let me get down to the specific model we looked at in this project. Very simple. So it's a Lindbladian with a Hamiltonian, which is just a Zeeman coupling with a magnetic field along the v direction. And this is a large spin. This S operator can go above spin 1/2. And then we have two jump operators. So the first one simply brings spin to the North Pole. So it's like a damping. And the jump operator L2 is a bit more complicated, as you can see, that we have two spin operators here. So this is where the nonlinearity comes from. And we have a jump rate that brings spin down, but this rate depends on where the spin is on the Bloch sphere. So you can think that here's like you first measure SZ, and that determines the rate of bringing spin to the South Pole. So this is a single spin model, but you can think of it in the spirit of Dickey model. It's made of many, many spin 1/2s that preserves the total spin in the dynamics, right? So here we do not distinguish between classical limit or thermodynamic limit, because they're the same limit. We can take spin to infinitely large. Right, and this model has if I take the classical limit or thermodynamic limit of spin going to infinite, these equations of motion have a limit cycle attractor. So this depends on this parameter gamma, the ratio between the two jumps. When gamma is smaller than 1, there is a fixed point at the North Pole of the Bloch sphere. And when gamma is larger than 1, there is a stable limit cycle sitting somewhere on the northern hemisphere. And now let's look at the Liouvillean spectrum. So in the fixed point regime, this is what we see for a finite spin, but still quite large. So there are many points, and we are only looking at the slow relaxation part. So here there is a gap, which is quite normal, and you can see some like a wedge-like pattern. And this is actually quite universal if we go to the classical limit. So this wedge is filled with basically two bases. There are two relaxation rates, lambda, and you just do a linear combination of these two numbers, and you can generate this whole spectrum. So this is a general feature for a Liouvillean spectrum when you have a fixed point. And for the limit cycle case, it's more interesting here. For finite spin, we get a parabolic branch here for the lowest energy, for the lowest relaxation rate. And there are several other ones. So this forms the structure in the limit cycle regime. And when you go to the classical limit, this whole branch collapses onto the imaginary axis. So they become purely imaginary. They're equally spaced. The spacing is determined by the precession frequency of the spin, and it's a branch made of infinite number of points. So the first question we asked ourselves is this actually an infinite branch? And it is, and that is necessary because this branch, these points, form the angular momentum basis of this precession. So if you, right, we're going to the classical limit, which means we will get a point, an infinitely precise point that is running around the limit cycle. So you have a Fourier basis of angular momenta that is infinite. And we can also look at this tiny gap here for finite spin and see how it closes as we take the classical limit. So this is the gap. I just take this branch and zoom in. So this gap, we call it delta C. All right, so, okay, this is a side remark saying that for finite S, the steady state is a mixed state around the limit cycle with a width that scales with S, 1 over square root of S. But now let's focus on this gap here. And this gap closes as 1 over S. So this is when gamma is larger than 1 in the limit cycle regime. So basically, the way we understand such a dynamics is that this is a phenomenon of decoupling of two time scales. One time scale is this tiny relaxation rate. The other one is this precession frequency. So the spin is still precessing before the probability distribution spreads into this mixed state. This one. Yeah.
So if you have a steady state, which is essentially the red dot, at the very there is a steady state with no motion.
Right here, the limit cycle coexists with a fixed point. You mean the red cross? Which red?
Yeah. So the limit cycle is a possibility. In the one-two side, what is responsible?
Sorry.
You said you had a gap. Yeah. So the gap is between the bottom ones.
Right. The gap. I take this branch, and so this is the origin. There is a fixed. There is a steady state, and I look at the immediate next point on this branch.
The state is the one that classically becomes the limit cycle.
So the whole branch becomes the limit cycle. The steady state is a mixed state of everything around this ring. So the steady state has no dynamics, but at the long but not infinite time, you have dynamics because of these other points. They have imaginary part, right? So it still oscillates. Okay, and in the classical limit, there is a nice way we can look at this system with the formalism of Fokker-Planck equation. And again, this separation of time scale shows you have a drift. So this second term here, and a diffusion of the probability distribution. So it's very clear from this animation that wherever you start, you drift towards the limit cycle, and then the wave packet diffuses, and in the end become this static mixed state. And exactly from this form, we can solve the spectrum, and you can see it's parabolic exactly up to the order of 1/s. So the wave packet, the probability distribution looks like this. It's time dependent in such a form. So this gives us the parabolic shape of this branch, and also the angle dependence of the probability that goes as square root of t, which is exactly diffusion. So this feature is quite universal. You have a parabolic branch that can be seen as a signature of a limit cycle regime. So I've told you about the spin model, and we also checked the boson model, distributive Bose-Hubbard dimer here. I will not go into the details, but basically also we get a parabolic branch, and in the classical limit, they collapse. So these blue points are on the branch, and in the classical limit, all these gaps close and they collapse onto the imaginary axis. Okay, so that's about the limit cycle. And between the fixed point and limit cycle, there is the Hopf bifurcation. And here the dynamics shows a critical slowing down, which is also quite interesting. So let's look at the, right. So you can see it approaches the North Pole very slowly and also oscillating at the Hopf bifurcation. And here the spectrum looks like this. Note that I've rescaled the real axis with square root of s. And here we have the same gap defined as before on this parabolic branch. And another gap we can define is the distance between the parallel branches. I don't know if you can see this. Okay. And for Hopf bifurcation, both gaps will close. So here's, we already know that the gap delta C closes, right? And at the bifurcation, it closes as 1 over square root of s. And delta P also closes when gamma is tuned exactly to the bifurcation point. Like this. And together, this will give us the dynamics of critical slowing down. And we can view it in this way. So if I write down the decomposition of these eigenmodes, right, and measure observable, which is the distance to the North Pole here, this R, and we expand it with the eigenmodes or eigenvalues. So here, because the spectrum is dense enough, you can take the summation into an integral, and given certain distributions of the eigenvalues, this integral can give you this algebraic dependence with time, and the basically the feature of all these branches will collapse is necessary to give rise to a critical slowing down. Okay, and the important difference between Hopf bifurcation and limit cycle is that in the limit, they both have decoupling timescales, but they decouple in a slightly different way, different ratio. In the case of limit cycle, you approach the limit cycle with a radial velocity that goes to 0, but the angular velocity, this frequency, stays constant. So the ratio between the two is 0 when you get close to the limit cycle. In the bifurcation case, we're approaching the North Pole. And here, the ratio between the radial and angular velocity scales with the distance itself. So, which is also consistent with this algebraic critical slowing down. Okay. Just to show you the cartoon again. Yeah. Right, so basically this is all. As a summary, like we see very generic spectral fingerprint corresponds to this attractor dynamics in the classical limit. For the fixed point, we have this wedge with a constant gap. In the limit cycle case, we see these parabolic branches and the gap collapses in the classical limit. And for Hopf bifurcation, a bulk part of the spectrum all collapse onto the imaginary axis in the classical limit. Yeah, and for something we're gonna do next, in this model, we know so far it's a Lindblad, but we know if we add some drive, it could display periodic doubling and even chaotic dynamics, so we would like to see what happens to the spectrum. And also, we would like to use this model as a, because it's simple enough, to explore how to use nonlinear dissipations as a source to stabilize maybe time crystal or quantum states. Yeah. Thank you.
I think I missed the part. How did you exactly get to those Lindbladian operators in the first?
You mean
In this
physical
class, yeah, like what is your class, your environment,
No, we didn't do that. So here we just write down. Yeah. No, this is just a model we write down.
How did you, could you maybe say at least the reasoning?
Yeah. So I would like to draw the analogy to this spin dynamics. Right, as I said, if you have damping and pumping, they compete. You could stabilize the cycle. So here, the minimal ingredient is first, I have one jumping up, one jumping down. Right? So they compete, but also I want the composition to be nonlinear. So let's add another order of operation.
Okay, But this SC just measure the state, right? So if it's some state, it's going to relax at different time than if it's another state.
Right, exactly.
I see. Okay. Thank you.
You mentioned there is a connection array with a crystal. Do you think that this mode somehow can be sort of modified or pretend towards some kind of crystal?
Yeah, so I think here you can also call it a time crystal in the thermodynamic limit.
Well, okay.
Yeah, but only in the like
Like in the boundary time crystal.
yeah, like the boundary time
Which is
crystal.
a classical cycle in a way.
Yes. The difference is, I think the boundary time crystal paper is protected by symmetry. So there's some symmetry that gives you, that selects out the trajectory. But here it's the nonlinearity that selects the trajectory.
Other questions? If not, let's
Need to change.
Come? Sì.